The 74LS181 is a 4-bit arithmetic logic unit, aka ALU, from the 74LS chip series. It was first introduced by Texas Instruments in February 1970 and was the first complete ALU on a single chip. It's capable of performing a variety of logical and arithmetic operations including AND, OR, exclusive OR, subtraction, and addition. Some key features include two 4-bit wide inputs, active low, notated as A and B, a 4-bit wide output, also active low, notated as F, a 4-bit wide function selector, notated as S, a mode control input between logic and arithmetic operations, notated as M, a carry in input, a carry out output, and an open collector output, notated A equals B, that I will discuss later. Additionally, the ripple carry output and inputs allow for the chaining of multiple 74LS181 chips in order to perform higher order math like 8-bit or 16-bit math. And the chip can also enter an abstract mode called subtract mode, where it can utilize the subtraction function to perform comparison operations between the two inputs. With that said, in more simpler terms, it is a chip that can do math. Let's take a look at it in action. So here I have a breadboard set up for the chip to help us control it. To give an overview of the items on the chip, I have on the left side several dip switches to control the chip. I have the A input, the B input, and the selector, the function selector inputs. And on the right side, I have some LEDs to see the output of the chip. Specifically, the red ones are the output F of the chip. And here I just have a 74LS04 to invert the active low outputs. And over here I have a yellow LED to show the A equals B open collector output, and then the green LED for the carry out. And down here I have some wires. The green wire is for the carry in, and the yellow wires for the mode select. Now, let me just place the chip in. Plug it to power. And let's take a look at some of the operations it can do. So if we turn to the second page of the datasheet, there is a handy chart to see all the operations that the 74LS181 can perform. If you take a look at the left side of the chart, you'll see various combinations for the function selector that you can input in, and combined with the mode select and the carry in, you're able to choose from a variety of different combinations or different operations that the chip can perform. Let's take a closer look at some of these operations. Let's start out with the logic functions. So if you take a look at the left side of the chart, you'll see that the logic functions are labeled when M, or mode select, is high. So if you take a look at the breadboard right now, I have all the inputs as low. The inputs are low, and mode select and carry in are low. So if we just select the mode to high, like this, we take a look at the first operation available. It's A with a line over the top. That means not A. So if I select all the selector inputs down low, which I already have right now, and take a look at the input A, the output should reflect not A, or the inverted version of A. So since they're all low, all the outputs are high right now. But if I start switching off and on the bits, the output will reflect whatever is being input into A. So as you can see, the first bit in A is high, so the output is low, and vice versa for the other bits. And note that the logic operations, for now, we will ignore the carry for logic operations. Once we get to the arithmetic operations, that's when the carry will become useful. Next up, we'll take a look at the function couple lines down, which is high, 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 low in the mode select. That is A, B right next to each other, which means A and B. So what we'll do is, let me reset the inputs for A and take a look at the modes of the function selector, and I turn these bits up high, 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 low, and we'll take a look at the inputs. So right now, since both of the A inputs, or A and B inputs, are low, according to the AND truth table, the output should also be low. Oops. Once we take, let's say we take the first A input, make that high, still nothing shows up. But once we input the first bit in B high, the output turns high. Let's try some more. High. Still nothing. High. Okay. As you can see, there are other operations that we could cover later, but now let's move on to some of the arithmetic operations. Okay, so I've reset all the inputs to low on the breadboard, and now let's take a look at the arithmetic column on the function table. So if we look a couple lines down from the top, you'll see there's a function for A plus B written out without the symbol or the cross for plus. There is A plus B, and that is high, low, low, high. And you'll notice that the mode select and the carry in are low. So if we just set the function selector to high, high, low, low, high, we'll see what happens next. So this time the carry input or the carry output will be used, and I'll discuss the A equals B output in a little bit. But if we take a look at the inputs, right now we have 0 and 0. So right now we're doing addition. So 0 plus 0 is obviously equal to 0. But if we input 1, now we have 1 plus 0 is equal to 1. Switch on the first bit in B, and now that first light turns off and the second light turns on. So we have 1 plus 1, 1 plus 1, and that is equal to 2. Now this is all in binary, so we just select maybe 5 plus 0 is equal to 5. And down here, maybe 5 plus 4 is equal to 9. But maybe we have 13 plus 4. What's 13 plus 4? 17. And as you can see, we have the carry bit now on because that bit overflows into the 16's place. And we have 1 over here, so this is 17. Now moving on to subtraction, which is probably the most complicated operation for the chip. there is a function input for subtract. If you take a look at the arithmetic chart, a couple lines above a plus b is a minus b minus 1, and that's low, high, high, low. So we just go input low, high, high, low, just like that. And for now, mode select and carry are both low, but if we take a look at the output right now, what we have actually is 0 minus 0, 0 minus 0. And right now it's displaying all ones, which doesn't seem right at first, but what it actually is displaying is a minus b minus 1. So remember that it's a minus b minus 1. So we're subtracting the extra 1. So what we can do instead is we can actually add a carry in, set the carry in high, and that will actually reflect the something that we might be more useful, which is a minus b. So now we have low, high, high, low in the function selector and the carry in as high. And now we have a subtraction operation set up for the chip. If we just put in some inputs for a, maybe 4, 4 minus 0, 4 minus 0 is 4, maybe minus 1. Okay, 4 minus 1 is 3, maybe 4 minus 3 is 1. And note that this chip will be working in 2's complement. So what we're going to do is take a look at the leftmost bit for the sign. So just to demonstrate that, what I can do is reset all these inputs, take a look at the A input, set it to 2. So 2 minus 0 is 2. And then actually set the B input to 6. If you're familiar with 2's complement, right now the output is outputting 1, which is the sign bit, 1, 0, 0. So that is going to be negative 4 in 2's complement. Let's try another one. Let's say maybe 1 minus 1. That's 0. But maybe we set this next bit high. 1 minus 3. And if you're familiar with 2's complement, there's 1, 1, 1, 0. And that is negative 2 in 2's complement. So note how the a equals b and the carry input have been flickering on and off throughout the demonstrations. So now I'm going to discuss something that is mentioned in the datasheet known as subtract mode. So if you take a look at the second page of the datasheet, there's the description. It talks about the subtract mode combined with the a equals b output and the carry out signal. So to just summarize a little bit of what the datasheet is talking about, the subtract mode, all that is just this function signal right here. Low, high, high, low. And all the datasheet is talking about is technically you could use the fact that the size of numbers and subtracting them between each other to determine whether or not they're equal, greater, or less than each other. So in reality, what the datasheet is talking about is that 74LS181 can utilize the subtraction function to perform comparison operations. And that's exactly what this A equals B is trying to do. So in reality, all the A equals B output is basically a zero flag, or it lights up when all the outputs are zeros. So you can see how you can use this to compare the bits or the numbers from the different inputs. So if we take a look at A right now, A and B are both zero, and since it's in subtract mode, and we're adding this one to make it A minus B, 0 minus 0 is 0, so the output is 0. And if we just take a look at the yellow LED, which is the A equals B, it is lighting up, which means that the output is 0, or in subtract mode, means that A is equal to B. Now, of course, we can cycle through a couple more inputs to see this in action. So now A is 1 and B is 0. So if we take a look at the output, if you were just trying to subtract stuff, 1 minus 0 is 1. But take a look at the A equals B output, and it turns off because now this is not 0. The output is not 0, and so A is not equal to B. We can turn it back on by making A or B equal to 1. So now 1 minus 1 is 0, output is 0, and A equals B is turned on. So now that we've just seen how the equality works in the subtract mode, the datasheet also talks about how you're able to use the carry output for telling whether or not A is greater than or less than B. So in conjunction with the equality or A is equal to B signal, you're able to also determine whether or not A is less than or greater than B. So how that works is it's pretty simple. So if you take a look at A, or if you take a look at the A equals B signal right now, it's on. If that is on, then both inputs are equal. However, let's say we maybe turn A on. If the equality is off, then all you have to do is check the carry. And if the carry is on, then A is greater than B. So this works for all the other size inputs. So if I just make A even bigger and maybe set B to maybe 2, A right now is 5, and or B and is B equal to 2, you can see the equality signal never turns on, but the carry light is on. So now this also works to check whether or not B is greater than A. So if we take a look at the carry signal, if I set B to maybe 1 and A is equal to 0, you'll notice that the carry turns off. So basically how it works, and then if we just take a look, turn A back to 1, both lights turn off, but we look at the equality signal first, and that's on, so that means that both signals are equal, or both inputs are equal. So basically how it works is you're going to first check if the equality signal is on. If it's on, then both inputs are equal. But if it's not on, then you check the carry out signal, and if it's on, and then the A input is bigger than or greater than the B input, and if you check the equality and it's off and the carry is off, then where both of them are off, then B is greater than A. So remember, this all only works in subtract mode, or when your chip is selected to do subtraction and the carry in is high. So instead of doing A minus B minus 1, you're doing A minus B, just regular subtraction. So, and then another thing that I want to address is some difficulty that some people might have while hooking up some similar setup of mine. The 74LS181 has the output for the A equals B is not your normal input output. It's something called an open collector output. And just a really simple explanation of it is that when it's normally in place, it's not connected to anything at all. So it's neither if you use like a multimeter to detect the voltage, it's neither high nor low. So like it's open, and then then a way to hook it up to something like an LED. All I have right now is, you can see right here, is I have a pull-up 220 ohm resistor connected over here to the LED, and it's just right there. That's the A equals B pin, and the LED of course is connected to ground. But right now all I have is this LED that lights up once the output pulls the signal in. So that's the open collector output. All it is, so you just need to connect it to some sort of pull-up resistor, and you should be able to collect the signal by connecting on a separate wire. So now that you've seen the chip in action, let me acknowledge that the fact that the chart given by the datasheet is pretty confusing. So if you take a look at it, there are various functions that I couldn't really imagine that you would use in any scenario. Like for example, maybe what is this? A and B plus A or B. Stuff like this is all over the function chart. So as you can imagine, you can almost consider some of these operations useless and redundant, and there are a lot of duplicates in the chart. So luckily, I found someone on YouTube that also shared the same sentiment, and like for me, he actually created a filtered down version of the chart, and as thankfully shared it to all of us to use. So I will link his channel in the description, or the video in the description. As you can see, he has simplified the chart down a lot, and I've just annotated a little bit. So if you take a look on this left side, of course I've chosen the active low operands for my 74LS181, and you just can see he's really just removed all like the useless operations and the any duplicates, and all the logic or everything is rewritten in a more understandable manner, not than the symbolized version of logic, with the symbolized pluses and the lines on top. So this is really easy to use, and I will link this down in the description for anyone who may be interested in trying this out for themselves. So that is all for this video. Hopefully it has given you a good idea of how the 74LS181 works and how you may use it. Overall, it's a pretty clunky chip which packs in a lot of features, both useful and useless, but in the end it gets the job done, and if all you need is for a chip to do some basic math and logic operations. Although I did go over a lot, this video is probably not a comprehensive list of all of the 74LS181's features and use cases, and I've linked, as mentioned previously, other videos as well as several other references that you may find useful in further understanding the chip in the description down below. That's all for today. See ya.